Now we are in 8.4, looking at parametric equations. And from here on out, we are going to change a little bit of the direction of the course because everything we dove up to this point has to do with trigonometry. But this second part of the course, it's a small part, but it's more algebra based, I would say. There's going to be very little, even in this section, we'll introduce a little bit of trig functions, but it resembles a lot of algebra. And the chapters coming also have the algebra involved in the content. So starting with parametric equations, and just start with defining. So parametric equations help describe the movement slash direction along a curve. Now, these curves are going to resemble a lot of algebra curves that you did, like parabolas, ellipses, and so on and so forth. But the main idea of what a parametric equation does is describing that direction slash movement along a curve. That's what we're going to mainly focus on. And what creates that direction? It's going to be the parameter. So it's called parametric equation because there are equations that have a parameter. And this is the form that you'll see the equations. So things are going to be more in rectangular form, shape looking, but they're considered parametric. And they have a parameter, and this is what creates the movement and direction, or what shows the direction of movement. And the parameter is this t. So we get our x and y coordinates from this function f and g of t. And we're going to see some examples that show us this movement and direction on these curves. So let's look at an example. I have it written out here already. So if you notice, we have our x and y table, but we're going to add this column of t because this is our parameter. And we want to go in this direction, meaning that we want to go from smallest to largest. So that would mean starting with, let me put t in a different color. We'll start at -2, -1, 0, 1, and then 2. And I want to keep this order as I plot it on my graph as well. But the rest from here is what you've done before. What do I mean by that? It's how we did in algebra, right? You would take this value and you plug it into your equation. But right now we're going to plug it into this equation for x. So that's going to be 3. It's going to be 3t squared. We're going to do that for all of them. So I'm just going to start setting it up for the sake of time. Every time I plug something in, I always prefer to replace it with a parentheses so that when I plug things in, it makes it more efficient and less likely for me to make any errors. Now, of course, negative 2 squared, well, and then the negative in the parentheses, it gives me 4, times 3 is going to be 12. Negative 1 squared is 1, times 3 is 3. 0 squared is 0, 3 times 0 is 0. 1 squared is 1, times 3 is 3. And 2 squared is 4, times 3 is 12. And this is going to be our x-coordinate for our graph. Let me make that a little bigger. These are all my x-coordinates. Now we have to make our y's, which is just 2 times t, 2 times t, 2 times t, and so on. Like I said, I like to replace my variable with, in this case, my parameter with parentheses, so that when I plug in, I don't make any small errors. And that's going to give me negative 4, negative 2, 0, 2, and 4. And this is going to be, all these are all my y coordinates. And then we just have to graph. But you want to make sure when you graph, you pay attention to your first ordered pair, second, third, fourth, because that is the order that we're going to sketch the graph, and that direction in that order is the movement. So starting with 12, which if you notice here, that's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and then 12 is this point here. And then it's going to be 12 and negative 4, which is down here. So our first ordered pair is going to be right here. And then we have 3, we jump big, and then we have 3 and negative 2. 0, 0, positive 3, positive 2, and positive 12 and 4. Now, hopefully, this is clearly not a V, because we have to get to this point in the next one, and same here. Hopefully that reminds you of an algebraic graph, which was a parabola. But this is a sideways parabola. Now, if you remember, a sideways parabola happened when you had an equation where your y was squared versus the x being squared. And I say that just because, so this isn't the exact graph, but make a quick note that when you had a sideways parabola, it was when you had a y squared instead of y equals x squared. Now that's going to be important for a little later. I just want to keep that as a side note for something we're going to do. And like I said, we started with this point here, and I'm talking about this one. So that means the direction of this curve is this way. And then we followed this path. And this definitely helps us understand the movement, right? And the idea is because the purpose of these equations that you did in algebra is because there's a lot of things that mimic these curves, right? And when we think about things in the real world, a lot of shapes have parabolic shapes. A lot of graphs follow the shape of a square root function, follow the shape of an exponential, of a logarithm. And because of that, things in the real world are not always at rest. Things have movement towards them. So this definitely helps us determine that movement, right? That direction. There's definitely a difference between, if you want to call this like a push versus pull concept, right? So the idea is that we can now sketch a graph, right? And then determine its movement, whatever that might be useful for. And at any point you can pause the video and try one of these examples. But here's our next problem. So once again, I'm going to use my same setup. You can use any numbers, right? I'm just choosing nice ones to make things more efficient. But I have my X and Y table, and we're going to plug into our equation. So we have -2, and again I'm just going to replace with parentheses, plus 2, and since it's long, I'm literally just going to copy, because luckily I can, paste, to save myself some time. This way I can input all my values. So the first one, we know -2 times -2 is 4, plus 2 is 6. And then -2 times -1 is 2, plus 2 is 4. -2 times 0 is 0, plus 2 is 2. And then here we're going to get 0, and then we're going to get -2. Because -2 times 2 is -4, plus 2 is -2. And then we have all our x coordinates. Now we need to get our y's, which is going to be 4t squared minus 2. And like I said, we can take this. I'm going to copy just to make things less to make things a little bit quicker. So we can put the -2, -1, 0, 1, and then 2. So here, -2, 2 is 4, positive 4 times 4 is 16, minus 2 is 14. All right, and if you can do these calculations if you want, you can pause, do these calculations. But for the sake of time, I'm just going to input all the values. Right, this is just arithmetic. But once again, -1 squared is 1, times 4 is 4, minus 2 is 2. And now I have all my y values. But we're going to start with this 6 and 14. So this is 2, 4, 6, 8, 10, 12, 14. All right, let me put the numbers. So 2, 4, 6, 8, 10, 12, 14. If that helps. And same at the bottom. 2, 4, 6. And now help me put my very first point at 6 and 14. And then we have one at 4 and 2. And then we have another point at 0 and 2. Oops. I missed. So we have 4 and 2, and then we have 2 and -2. Sorry, I missed 1 point. 0 and 2. And then we have another point at -2 and 14. And if you notice, this is going to have that similar shape as our previous one. But now this is a parabola pointing upward. So that does change things a bit. Once again, when did we get a graph this way? Like I said, I'm just going to make small, quick notes that this is when you had x being squared. And like I said before, that's going to mean something at the end. But once again, we have our curve facing, we started at the top right, and then we can see our direction. It's important to keep it because we are trying to focus on the direction, the movement along this curve. And hopefully this reminds you of the equation y equals x squared, because we are eventually going to try to take these parameters and rewrite them back into their rectangular form versus their parametric form. And now, move our next example. And this is where, like I said, we'll have some portion of some trig in here. Not a whole lot, but we will see some. And our parameters from 0 to 2 pi, so just one full rotation. And right, I always liked using what I like to call my four corners. So I'm gonna stick, I'm gonna stick to this pattern, right? I didn't write 2 pi just because 2 pi would be back at 0 again. Again, you can choose pi over 4, all those other ones. I'm just starting with these first few. Just like before, we're going to have 5 times sine of t. This is my x. I have 5 times sine of t. I just put parentheses where the argument should be. So then I'll copy. So I can just paste, make it quicker. Instead of writing each one of them out. So 0, pi over 2, pi, 3 pi over 2. So remember, sine of 0 is 0 times 5 is going to be 0. Sine of pi over 2 is 1 times 5 is 1. Sine of pi is negative 1 times 5 is negative 5. Oops, I made a mistake. That's what happens when you go too fast. Sine of pi over 2 is 1 times 5 should be 5. And sine at pi is 0, not negative 1. Cosine of pi, sorry. Sine of pi is 0 times 5 is 0. Sine of 3 pi over 2 is negative 1 times 5 is negative 5. So make sure you're not trying to just speed through these. Sometimes we mix them up, so be careful. Cosine of, now we're doing cosine. So let's not mix that up. And let me input all my y's. And that's, of course, is going to be 0, pi over 2, pi, 3 pi over 2. Cosine of 0 is 1, times 4 is 4. Cosine of pi over 2 is 0, times 4 is 0. Cosine of pi is negative 1 times 4 is negative 4. And then cosine of 3 pi over 2 is 0 times 4 is 0. And now we have our y values. And we can just plug these in. Let me move a little bit. So my first point is at 0 and 4. Right up top. My second point's at 5. Five and 0, and then we have another point at 0 and negative 4. Then we have another point at negative 5 and 0. Now hopefully you can recognize that this gives me this circular shape. But if you notice, it's not a perfect circle. Because if it was a perfect circle, that shape would be here. But this is actually more oval. And hopefully you remember an oval shape like this is called an ellipse, right? It's just a little bit longer on the sides. If it wasn't, we would have had a perfect circle. But we did start up top, and we went in this clockwise direction. So that tells us the movement of this ellipse. And that's it. That's really all we're going to be doing for this section. All I'm looking for is being able to sketch these graphs and establish the movement. Now, like I said, if you remember, this was an ellipse. And in algebra, the equation of ellipse was in this form: x squared over a squared plus y squared over b squared equals 1. That was your standard, not the general equation, but this was an ellipse centered at the origin, which we have here. Now, why do I keep highlighting these? And that's because we can actually rewrite all of these parametric equations back into their standard form. So for example, let's rewrite these into rectangular form. Now, how do we do that? The goal to rewrite back into rectangular form is to remove the parameter. So let me show you quickly with an example. We'll do that very first problem. And there's different ways of doing this. There's not just one way of rewriting. But having these two equations, the goal is to figure out how to use both equations to no longer have this parameter. So the quickest way is remembering the concept of a system of equations. Remember, if you have two unknown variables, you need two equations. That's when you dealt with systems. So something I can do is I can take y equals 2t and rewrite it as t is equal to y over 2. And how do I get that? I can divide 2 to both sides of this equation. What that allows me to do is then take t and plug it into my first equation, which gives me x is equal to 3, and then put in parentheses 2, and then y over 2 for x. And then that's going to simplify to x is equal to 3y squared over 4. Now, that's because if you remember from algebra, when you have a fraction inside of a power, you can apply the power to both the numerator and denominator. And this is the this is the rectangular form of that parametric equation. Now, if you remember, I did say, note how this has a y squared in it. The benefit of that is because it was this parametric equation, and I said in algebra, the sideways parabola had a y squared. The upward parabola had the x squared. So it helps really, it doesn't tell me that I'm right, but it does help with guiding your thinking and your understanding. One more quick example to end this long video. is we'll do that last example we did, sine of t, just to kind of illustrate different examples or strategies to eliminating the parameter. Now, in this example, we can eliminate the parameter by trying to isolate t, but the problem, if you remember, to isolate an argument, we have to use an inverse. Now, once again, the benefit of knowing the parametric curve and its movement is I know this shape. This is supposed to make an ellipse, which an ellipse has the form of x squared plus y squared in its original rectangular form equation. If I were to try to isolate t by using an inverse, that would then mean I have to plug an inverse into this sine. But the original equation for an ellipse doesn't have sine and cosine inverses in it. So I have to take a different approach. And dealing with trig functions, in some scenarios, we can isolate the t and plug it in, and that makes things work. Or just isolating your cosine. If there's a substitution that can be done to help eliminate either the function or the parameter together, we can use, right? Here, we probably don't want to isolate just t because that leaves us with inverses. But if we make a quick note or recall, I know that there is an equation that involves sine squared t plus cosine squared t equaling 1. And I always said we can actually rewrite that power outside versus inside, except when there is a negative. Because remember, for negative, it means inverses. It does not mean 1 over sine of t. Absolutely not. That would get you automatic 0. But any other power, you can treat it as a power, but the negative 1, that's not really there as an exponent. It's there more for notation to represent an inverse. Now this way, I recognize that, wait, I have a cosine, I have a sine. Instead of isolating just t, I can isolate. So to start, I can rewrite sine of t as x over 5 and cosine of t as y over 4. And then that allows me to make my substitution as x over 5 squared plus y over 4 squared equaling 1. And that simplifies to x squared over 5 squared plus y squared over 4 squared equaling 1. And this is the rectangular form. And you can notice because, and I didn't apply the power yet, I just distributed to the numerator and denominator. And if you notice, this is 5 and 4. The 5 is under the y. Sorry, the 5 is under the x. The 4 is under the y. And we can use that because in the x direction, we go 1, 2, 3, 4, 5 left. 1, 2, 3, 4, 5. Sorry. 5 left, 5 right. Up 4, down 4 on the y. And that's exactly what this is telling us. So I said, there's multiple ways of approaching it. It's not always this identity. Maybe you can use other trig identities, either isolating t or just isolating the function on its own. Because I'm still, by doing isolating sine, I'm still eliminating the parameter, but I'm also eliminating the function. This, since it's a linear equation, I can just isolate t. This one is a little more complex. I isolate the whole function. So I'll give you more practice for these. This will definitely be on our exam, so keep in mind on that.